Yep. Let's do that. It okay? Yeah. Can you change the slides now?
Yeah. No, I have to click there. Yes. Yes, it works. Okay, can you bring it up? Okay.
Okay. So the first talk will be given by Marco di Liberto, and he will be talking about emergent orbital physics and parallel phases. So please,
Okay, let me start by thanking the organizers for giving me the chance to present these results. And the topic that I'm going to present is it's a strategy to have an orbital physics, and I'll tell you what it means in realistic setting up to the strongly interacting system, which is something that is in a way missing from experiments, and we propose a strategy to do that. And this actually this plan falls within the agenda of quantum simulation, in the sense of having a sufficiently large a sufficiently broad toolbox of methods and strategies, at least in terms of analog quantum simulation, to be able to build up from engineered systems all the type of models that many models that we're interested in understanding, which could be either bosonic, fermionic, spin models, and for example, today Francesco was telling us about the SUN models and so on. In the toolbox for quantum simulation, something that is actually fundamental is to be able to control time reversal, because several phenomena in physics depends on the presence or absence of time reversal symmetry. And of course, the main example is given by quantum Hall effects, which typically occur for charged particles. So in the idea of doing quantum simulation of charged particles, but using neutral systems like atoms, a lot of strategies over the years have been developed and put forward. For example, engineering complex hopping phases that play the role of Aharonov-Bohm effect and thus magnetic flux, or mimicking gauge fields by making the rotation, fast rotation, a quantum gas in such a way that the Coriolis force is kind of mimicking, let's say, the effect of a Lorentz force. Or more general strategies based on driving, where you imprint time reversal symmetry breaking by and chirality by external drives. So in what sense time reversal symmetry can be interesting? Well, in particular, in the case of interacting systems, so I'm skipping the single particle physics and all the interesting Chern number results that many people already know. In terms of interacting many-body questions, realizing systems like fractional quantum Hall effects, where interactions cause the presence of non-trivial quasi-particle excitations with fractional statistics, and that can be used, for instance, via braiding for doing even quantum computation operations, is a holy grail and an important scope of the entire community. And very recently, in this direction, there have been a few experiments, either in polariton case, Jonathan Simon, and cavities, or in optical lattices, either fermionic or bosonic by the group in Harvard by Marcus Greiner and Selin Yokim, where a few particles have been prepared in a Laughlin state, a fractional quantum Hall state of just 2 or 3 or 4 particles, up to in the polariton case. However, all these examples assume that we break by hand time reversal symmetry, and therefore we have to build, let's say, the toolbox to do that breaking by hand. But we have another option, and the other option is that actually time reversal symmetry is broken spontaneously, like a symmetry breaking mechanism, not occurring for U1 symmetry or other ones that you're usually familiar with, but for time reversal. And one of these examples was proposed actually by Raghu, which is the same Raghu that Ronnie Tomali yesterday was advertising for another topic, and the group of Shuchen Zhang. For example, the occurrence of a quantum Hall effect, anomalous quantum effect, caused by symmetry breaking and interactions. And in cold atoms, we actually have examples of spontaneous time reversal symmetry breaking phenomena when we look at physics in higher bands. Then this is will be, let's say, the focus, with the goal of ending up here at some point in the future. So the brief outline of this presentation is about the physics of p-bands, the building block that we are proposing or we're discussing this, which is pi-flux plaquette, and then some dynamics that occurs, like an impurity that is can witness the breaking of chirality, and the possibility that via this scheme you can enter a Mott insulator phase, which has angular momentum, actually, a chiral Mott phase. And then I will conclude more on phase diagram opportunities and state preparation and measurement. So why p-band physics is interesting? Usually we are used to, for let's say in optical lattices at least, to load atoms in the lowest orbital of the single site, the s orbital. But we can imagine actually to promote all the particles to the second orbital, the p, and prevent, or let's say, assume that no occupation of the s occurs for sufficiently long time. In p bands, differently from the lowest band, now you have, for example, in 2 dimensions, you have 2 orbitals px and py. So there is orbital degeneracy and an orbital degree of freedom coming up. How does the tight binding model look like, and does the corresponding physics originating from it? Well, the hopping part is just orbital hopping. There can be, of course, different amplitudes depending if it's the px orbital or the py orbital. But the most interesting part is the interaction, because besides the usual density repulsion that occurs also in the lowest band, there is a new term, this L² term, which couples actually the 2 orbital degrees of freedom, px and py. And in terms of harmonic oscillator creation operator, this is actually the angular momentum operator perpendicular to the 2D plane. Now, I would like you to pay attention to the fact that there is a minus sign. So a positive interaction U corresponds to having a ground state which favoring an angular momentum to be maximum. Because if you maximize angular momentum through the minus sign, you minimize the interaction energy. So the result is that you create angular momentum in the ground state, which means that on each side I of the optical lattice, you have a condensate, let's say if you have a condensate phase, which has a vortex structure. So the ground state of this Hamiltonian is a vortex ground state. And this is, of course, simple because you see, since particles are repelling each other, a vortex is the one structure that has the minimal overlap between the 2 particles in the middle, because there is a hole in the middle. And that's why a vortex solution minimizes the energy of this interacting system. Okay. What we propose? Higher bands have been reached, of course, by the group of Andreas Hemmerich a few years ago, but it's hard to imagine that one can go to the strongly interacting regime, at least unless one finds out a good strategy for that, because particles sooner or later will decay down. The stronger the interaction are, if you want to go to the strongly correlated regime, the faster or the more likely the particles will decay, and therefore it's pretty probably impossible to increase interactions above a certain threshold. So we said, okay, let's think about a different approach. What if we keep using lowest band, the s orbitals, but we try to use them to encode the sort of p orbitals in them in an entire plaquette, to use the entire plaquette as an object that encodes p-band. So you have bosons hopping and interacting on the same side. So it's a simple Bose-Hubbard model. But now I insert a pi flux in it. Pi flux means that this hopping here has a different sign compared to all the others. And inserting a pi flux in the cosine potential energy dispersion means that you're shifting by pi over 4. Momenta are discrete. And therefore, if you look at the energies of these objects, you see that all the single particle solutions are twofold degenerate. And this opens the question, what if I exploit this double degeneracy and this gap here to make a theory for the lowest two modes in the full plaquette? Does this correspond to a p-band type of model or at least the same phenomenology? Well, the orbitals, since these are block states, they are extended. They will overlap. And thus the interaction U will couple with, so they will be coupled. So what we do is we project the Bose-Hubbard model to the lowest two orbitals, D1 and D2, and we obtain for this single plaquette this many-body model, which contains, of course, the density-density interaction, but then the same angular momentum term that we saw before for these two orbitals, D1 and D2. So the same mechanism occurring in p-bands could be reproduced or mimicked in the lowest s orbital of a pi flux plaquette, even in triangular plaquette. But here we focus on the square lattice case. Now let's gain a bit of intuition on this single plaquette. For the spectrum is easy to compute because the angular momentum doesn't change the number of particles, so it commutes with the Hamiltonian. I can go to the basis of the angular momentum states. So the plus chirality and the minus chirality eigenstate can be used to construct any many-body wave function. So how do you construct it? Well, you put n plus particle in the plus chirality state, n minus in the minus chirality state, and this times the entire spectrum. And of course, since there is a Z2 symmetry where I exchange L with minus L, the many-body spectrum must be twofold degenerate, which is what you see from exact diagonalization here. This was actually obtained with Q-spin. Thank you, Maren, for building up the library. Okay, so how does the ground state look like? Because of this term that wants to maximize angular momentum, you have two possible ground states. One in which I put all the n particles in the plus chirality state, or the opposite, or a linear combination. And of course, I can also gain intuition on what is the excitation, because the excitation corresponds to taking one particle from here, from the plus chirality, and moving it to the opposite chirality. So if I reduce the angular momentum of the ground state, I will create an excitation. And the energy of the excitation has two contributions that one can derive from this expression, a mean field contribution, let's say, and this is the correction to the exact solution. Of course, I can increase this gap by increasing either the number of particles or the interactions U. Okay, how to probe this physics? You can do spectroscopy, for example. You prepare the ground state and you try to see if there is an excitation with single particle excitation with lower angular momentum, or you could do a quench. What type of quench? For example, I prepare a chiral ground state. I add an extra energy gain in one of the states here, let's say this site number 2, and then I quench this impurity to 0. This is not an eigenstate, so we expect evolution. But what type of evolution? We are populating, I want to recall you, a state with a different angular momentum compared to the ground state. So the result is that the impurity will start rotating. This rotation occurs at G/4, the frequency we saw before. And you can benchmark it. In this case, we were in the almost classical limit with a lot of number of particles. So we use the GP equation and compare with the exact diagonalization. And the mismatch was actually studied as a function of the number of particles, and the convergence is pretty pretty stable. Okay, now that we have kind of understood most of the single plaquette physics, we can move to the extended lattice, where we can do strongly correlated physics and move to really long range, let's say. What we take is this dimerized square lattice, where you have this pi flux plaquette connected to other pi flux plaquette by a weak bond, J prime. And actually, all the plaquettes here have a pi flux. And this lattice here is actually being studied recently by the group of Taylor Hughes, Andrei Bernevik, and Vladimir Beran-Kazar, which is an example of a higher order topological insulator. You may have seen these corner modes that appear for such a model in some presentations. But we're not interested in the edge physics or in the topology for now, but instead on how to use this geometry to do orbital physics. And of course, what we discover is that since each plaquette can accommodate the vortex, what we obtain in the superfluid phase is a chiral superfluid. There is an array of vortices distributed coherently along the entire 2D lattice. One first difference compared to the single plaquette is now that the get mode we saw before, the first excitation, can actually decay by emitting phonons. And this decay rate can be in a way controlled by interactions, and that allows to see the existence of this get mode because it is finite, the value, and it can be compensated the decay lifetime by making J prime small. So far it's the weakly interacting regime, but then we would like to see what happens in the strongly interacting regime. And for this case, we know that a strongly interacting regime means that the interaction U becomes of the order of the only kinetic energy scale, J prime. And from p-band physics, we also know that there should be a transition from a superfluid, the one we saw a moment ago, to a Mott insulator of p-bands, however. And how does the p-band Mott insulator look like? Well, it looks like something that was also discovered a few years ago by Parmecanti, the so-called chiral Mott insulator. And phase which has a gap, but has also angular momentum in its graph. And indeed, if you study with DMRG this problem at some point, when you increase interaction U, you see that the fidelity susceptibility shows a singularity, showing the presence of a phase transition. And this is, let's say, happening at the same time as the charge gap opens up. So we enter a phase with a gap, an insulating phase, an incompressible phase. But what type of phase is it? Is it chiral or not? So for that, we studied actually the loop current, which means we take the current operator between two sides, and then we sum up in, let's say, clockwise or counterclockwise, all the current contributions around the plaquette. We show in the paper that actually this loop current is equivalent to the angular momentum operator, 1-to-1, at least in a certain degree. And the DMRG results show actually that when you cross the transition and you go from a superfluid to an insulating phase, the angular momentum actually remains finite. So we enter this phase, which is chiral and insulating. And all of this also exploiting this dimerization that allows to separate local plaquette currents from the rest of the lattice. Okay, so developments that have been that we are doing right now are, for example, understanding a little bit more the phase diagram. For this, we're actually using cluster Gutzwiller ansatz. You need a cluster ansatz. For people who are familiar with Gutzwiller, usually it's a product state, single side product states. But here, to capture the Mott insulator, the chiral Mott insulator, which requires the entire plaquette, you actually need the wave function that represents correctly the entire four sides. So short-range correlations in these ansatz are actually exact. And what we see indeed, it's depending on the filling. This is half filling, the one we saw in the previous slide, the chiral multi-insulator. Here outside is a chiral superfluid. There are other multi-insulators for quarter and three-quarter filling. And if you have one particle per side, one on each of the sides, then you actually find a trivial multi-insulator. So there are two different types of transition. One here in which time reversal remains broken, and one in which time reversal goes from broken to unbroken. So different universality classes. Okay, this opens up the question, can we possibly measure or prepare such a state? So we have been discussing a bit on this problem. We came up with the following scheme, which exploits the fact that this lattice is dimerized. So if this lattice was not dimerized, if you think of other phases in which loop currents are more extended, it would be much harder to prepare. But on a single plaquette, you could have control of the entire wave function, actually. And we exploit a method that was recently shown experimentally by the group of Monica and Sporter in Munich by using a double well control. So let's say you take a plaquette in this case, you split the plaquette into dimers, pairs of sides, and for every dimer you do two operations. Operation one is tunneling. It's a unitary operation which allows you to transport particles. For example, I start with one particle in this side, I apply a pulse of the right time length, and then I split 50-50 along this dimer my particle, let's say, with certain phase difference. Then I use another trick. I use another unitary operation, a tilt in the on-site energies, which allows me to control the relative phase. Remember, we want to build up a vortex wave function. So we have to control not only the density distribution, but the entire phase path. So combining a hopping process and these tilts to adjust the phases, upon in total 5 pulses, you can actually reconstruct the final wave function, which has a loop in phase. Notice a technical point. Usually, to do this dimer pulses, you could, for example, tilt the lattice in the x direction, tilt the lattice in the y direction. The last pulse is a bit different because you need to tilt the two dimers, but in opposite direction. So it corresponds to a sort of quadrant. Start like this, and you have to do like this. And this could be the more tricky part. And besides that, it opens up the question how to measure such a state. Again, this similar protocol for dimer. If you study the quench dynamics of the density in a dimer, basically by translating density into current via the continuity equation, and if you sample the density dynamics in time, you can reconstruct the current at initial time of this dimer. And this you can do for each pair of dimers and reconstruct the entire loop, which here we show it works pretty well. And actually, in this case, we extend the method that Monica's group did, which was based on going to the zero interacting limit. And here we extracted a formula where you don't need to quench interaction to zero to be able to extract the current value. Of course, the price to pay is that you have to sample the density oscillations in more time steps. At least here you need 4 of them, 1, 2, 3, 4. Okay, with this I will conclude. I showed how to do orbital order by using this strategy of exploiting a plaquette to mimic a p-band or a set of p orbitals. I showed that this actually allows to build chiral multi-insulating phase or strongly correlated phase, and you could use a single site control to prepare them. And of course, if you do it in parallel on each plaquette, and then you adiabatically turn on the coupling, you could prepare the many-body state. And now questions we are also investigating are excitations. You remember I was showing you that there are two types of phase transitions. So we would like to know the excitation spectrum across the transition. And if there is topology, there is a reason for topology, but I don't have the time to tell you right now. And also other exotic models like the 3D BBH model. So the same construction, but in 3D, which has some interesting features because the degenerate manifold is different than 2D. So there is more degeneracy, so more interaction channel. So you could get a higher spin model here. So I conclude acknowledging the collaboration. So this project started discussing with Nathan in Brussels. And then more recently, Maria and Lorenzo have been focused on the phase diagram and analyzing the variational wave function to describe ground state and excitations. And Andrei studied the state preparation protocol and measurement together with two particle physics. So with all, thank you all for your attention.
Thank you so much, Marco. We have some questions that are being asked.
Okay, so two questions. The first is, did I understand correctly that think about the coupling between neighboring pockets as being some sort of ferromagnetic coupling or anti-ferromagnetic? Ferromagnetic. Ferromagnetic.
Because the vortices that you get, they are pointing in the same direction. They are not separate.
Right. So if I think of like a super exchange process, what generates this ferromagnetic coupling?
So what you're talking about actually should happen in keeping the model solidarities.
Okay.
Which is not what we so the non-staggered vortex is just the fact that the band structure is a minimum of 0 exit. So the ground state will be translation invariant. Oh. That's why all the vortices for
Kinetic. Kinetic.
Yeah. This is different than p-days, where actually condensation is a momentum high. So we get
Last quick question, does your system conserve the angular momentum?
Yes.
Because I could imagine that at higher order, you have to break this.
No, because the CPT is pretty robust. At least a small we have in there. But you saw at some point I will show you the image result where the loop target goes down. So this reduces. So if you know, it's like the fixed point in the negative sense remains in the zero phase. So it's
Thanks for the one question. When you were in the ground state, yeah. So when you are in the ground state, you have like vortex. Okay, is that the place where I'm thinking of topology? So there is the two check master and then there is
no, because this modulator phase, even though it's not interacting, it's not correlated, it's still made of, I mean, the order is local at the level of plaquette, but not, should be no local at the level of the entire system. So what I did not show, which is the reason why we will investigate this further, and you actually know that from the discussion we had today, this PDH model has very curve. And since it has very curve, but of course I'm diversifying, so physical there is no topology, no general. But interactions can interfere in the curvature, and that may change to have, for example, the topology of non-insulator. The non-insulator plus with agents.
Yeah, thanks for this talk. I'm a little bit confused about the state preparation. So why do you need to use these fancy state preparation methods? Like the state you have is ground state system.
Yeah.
Is it very sensitive to temperature? Or like why would you just cool the system?
Well, you remember you need the 5 flux. In the 5 flux, it means you need a floquet scheme to generate the patterns. So the two things do not work well together. The heating can be severe. Whereas here, if you disconnect each plaquette from the other, the spectrum is basically super, there are a lot of gaps, big gaps, not a continuum of states. This way you can do together with the floquet scheme, the preparation of a single plaquette without heating in a single plaquette. The heating will come up later when you connect the system. But this is on a different time scale, and we don't have an answer to that.
Thank you so much. Yes. Проводил Zoom, yes.